In my last video, I talked about how to find critical numbers of a log function. And in this video, I'm going to be building on that topic and using those critical numbers to find local extrema of that same function. If you do want to check out that video, go ahead and click up there or over there. Not sure where it pops up, but you can go check that out and then come back and watch this video because these two topics are very closely related to each other. I'm going to be starting in this video with the critical numbers already found, and I'm just going to be going over how to actually use these critical numbers to then find the local maximum and minimums of the function. So if you already feel pretty good about finding critical numbers, but you want some more practice learning how to apply the first derivative test in order to figure out which of those critical numbers are mins and maxes, then this is the video for you. So be sure to stick around to the end. You should be feeling a lot better about this topic by the end of it. And without further ado, let's just go ahead and jump into the example and I'll show you what I'm talking about. So x equals 0 is going to be our only critical number of this function. Okay. The other thing that we want to be careful about is, are there any places where f of x or f prime of x does not exist, or any restrictions on the domain? We already figured out there's no places where f prime of x does not exist, but are there any places where f of x does not exist? In this case, we don't have any fractions or even roots, but we do have a log. We have a natural log. What you want to keep in mind is that you cannot take the natural log of some number that is 0 or negative. So we need to be careful to make sure that x to the fourth plus 27 is never negative. Well, raising something to an even power is always going to make it positive, or unless it's 0 to an even power is just 0. So x to the fourth will never be negative. So if we have some non-negative number plus 27, that's always going to be positive, which means this function, what we're taking the natural log of, is always going to be a positive number. So this function will exist for all x values. So the domain of this function, this original function, is all real numbers, right? There's no x values that are going to cause problems. There's no x values that we're not going to be able to plug into f of x. So as a result, really the only points that we want to put on to basically do our first derivative test to figure out where our local maximum and minimum values are is the one critical number of x equals 0 that we got. There's no restrictions in the domain of f or f prime, and the only critical number we got is x equals 0. So those are the only things that you want to put on your number line when you're trying to do the first derivative test. You're always going to start, that was not a very good line. You're always going to start your first derivative test by drawing a number line. Once you draw your number line, the only points you want to put on it are the places where you have a critical number or where you have restrictions in your domain of your original function. In this case, there are no domain restrictions. We only have a single critical number at x equals 0. So be careful. In this case, x equals 0 is a critical number, and that's why it's on our number line. A very common mistake I see people make is that they will always put x equals 0 on their number line. But the only reason you want to do that is if x is a place where your original function has issues with plugging x equals 0 into the original function, or if it's a critical number. In this case, it is, so that's why it's here. Okay, so now you can see this number line has basically been split into two pieces. We basically just split our number line for all x values less than 0 and all x values greater than 0. Those are the two domains, or basically, areas of x values that you want to test now using our first derivative test. The first derivative test says that we're going to take some number within each of these sections. So let's just say x equals -1 and x equals 1. Okay, it really doesn't matter what number you pick as long as you pick one number from each section. In this case, x equals -1 is in this section, x equals +1 is in this section. So then what we're going to do is we're going to take each of those numbers that we've selected and we're going to plug it into the derivative. That's why it's called the first derivative test. We're going to use our first derivative. So we're going to go back to f prime of x, this function right here, and we're going to plug in x equals -1 and x equals 1. So let me just start with copying this derivative down here. Now we need to plug each of these into our derivative. So plugging in -1 into this is going to give us 4 times -1 cubed all over -1 to the 4th plus 27. Plugging in +1 is going to give us 4 times 1 cubed over 1 to the 4th plus 27. Okay, now to simplify these, -1 cubed is -1 times 4 is -4. -1 to the 4th power is +1 plus 27 is 28. And then that's going to simplify to -1/7. Okay, and then let's simplify this f prime of +1 over here. We're going to get 1 cubed is 1 times 4 is 4. 1 to the 4th is 1 plus 27 is 28. So this is going to simplify to +1/7. If you are getting some value out of this video so far, do me a favor and hit that like button down below, please. It's a huge help to my channel so I can keep making more videos like this. So now that we have plugged in our critical numbers, or not our critical numbers, I'm sorry. Now that we have plugged in the numbers that we chose to the left and the right of our critical number, what does this tell us? Well, the first derivative test tells us that since f prime is negative at this x value, that means the slope of our original function is negative at that x value, because the derivative of a function always tells you about the slope of the original function at any given point. So in this case, if we know that f prime is a negative number at x equals -1, the slope of f must be negative at x equals -1. So if the slope of f is negative, that means it's decreasing at that point. Right? So our function f is decreasing for all x values within this interval over here. Okay. Similarly, since we know that f prime is positive for the x value of x equals 1, that means that since f prime is positive, the slope of f is positive. So the slope of our original function f is positive, which means it's increasing. So basically our function f is decreasing to the left of x equals 0, and it's increasing to the right of x equals 0. So if we're decreasing to the left and increasing to the right, we have a local minimum right there, because it's coming down and then going up over there. So this critical number of x equals 0 is a local minimum of this original function. Now, if we wanted to find the actual minimum values, we could just simply plug in x equals 0 into our original function and figure out what that value is. 0 to the 4th power is 0 plus 27 just leaves us with natural log of 27, which you could just plug into a calculator to figure out what number that actually is. But that would be a local minimum of this function, and that would be the only local minimum of this function. So that's it for that problem. Hey, you made it to the end of the problem and the end of the video. Bet you're feeling a little bit better about how to use critical numbers to find local extrema. If so, go ahead and hit that subscribe button, because if you found this video helpful, I guarantee you're going to find a lot of my other videos helpful as well, and we can just keep crushing it all term long in calculus. If that sounds good to you, just hit that subscribe button and that bell icon so you're notified when all my new videos come out, and I'll see you next time. Thanks.